So hello, chemistry people. So I wanted to go over a little bit about polarity and IMFs. So that's kind of the topics that we're covering this week. I'm doing this live, but most of you will be watching this on YouTube later. So I wanted to start with just by what the different IMFs are, the intermolecular forces, and in what situations they apply. And then I wanted to go through a couple of examples looking at some problems. So, if I'm just given the name of a formula here, so CH4, can I go from just this information to knowing what intermolecular forces are present in that molecule? And so we're going to start by first understanding a little bit what is an intermolecular force. So an intermolecular force is essentially the attraction between different molecules. So if I have, I had a picture here. If you look in this drawing here, this is a ice crystal. That's a water molecule, and that's a water molecule. And then they have all these little dashed lines between them. That dashed line is representing the intermolecular force. So just like the internet connects us to different computers like we're doing right now, an intermolecular force is a force that connects one molecule to another molecule. It's not a bond. So a bond is something that holds one molecule together. But when this molecule is held together and then another molecule is being held together, the attraction between those two is called the intermolecular force. So right there, in between there, that's a bond. This stuff kind of dotting around there, that's an intermolecular force. Okay, so what are intermolecular forces? What are the different kinds? How good are they? Which ones are present? Which ones aren't? That's what we're going to be going over. So I would say the most easy to understand intermolecular force is the dipole interaction, or the dipole-dipole interaction. So we practiced drawing polarity of molecules, and that was sort of to lead up to this. So here's, for example, this is a water molecule. It's got a dipole pointing up because we know that oxygen is more electronegative, so you get these little dipole arrows drawn towards the oxygen. And then as a result, you end up with this overall arrow pointing up. And so on this side of the molecule, where all the electrons are being pulled to, this side's going to be a little bit negative. And on the opposite side, where the electrons are being pulled away from, that's going to be positive. And so there you go. One side of it is negative and one side is positive, so I can erase all this other stuff. And I just need to know one side of this is negative and one side is positive. If another water molecule were to come along, then you have one molecule with a negative side and a positive side, and let's say I had another water molecule here. Well, this negative will attract a positive if available, because negatives and opposites attract. Yeah, exactly. Milton, your pictures are good. So then another positive side of a water molecule, bam, that's a positive side, that's a negative side. So here's a molecule, it's got a negative side. Here's a molecule, it's got a positive side. This attraction here, that's the intermolecular force, the IMF. And in this case, it's called a dipole-dipole interaction because this dipole pointing this direction and this dipole pointing this direction, they kind of line up so that they point sort of head to tail. And that attraction is it's called the dipole-dipole interaction. The bigger the dipole, so the more polar the bonds or the more polar the molecule, the stronger the dipole is going to be. And the strength of an IMF is really important because that's going to determine how well those molecules stick together. If we go back to that image of water, and I'll get there in a second, when water is ice, it's being held together really tightly. How do we know that? Well, because it's a solid. Solids are being held together tightly enough that they don't break apart unless you apply some force. As opposed to liquid water, it's the exact same molecules, but it doesn't have enough energy actually has too much energy to stay stuck together in ice. And so as a result, you get this liquid dispersion of the molecules going around everywhere versus a gas. So the phase of matter actually gives us a hint as to how effective the intermolecular forces are at keeping the different molecules together. So that's the dipole-dipole forces. I guess I actually skipped over this. This is good. Okay, so the dipole-dipole force is, as I said, it's the attraction between two molecules with permanent dipoles. So those dipoles here, this is exactly what I was showing, but with my drawing. This has a dipole pointing this direction. This has a dipole pointing this direction. They kind of align like magnets. We're on opposite ends, and then they attract to each other. This only happens in polar covalent molecules, and I'll get to more of a summary about this. But obviously, if I don't have a dipole, or if I'm not a polar molecule, then I can't have this kind of attraction. So only if the molecule is polar, and that's why we spent so much energy trying to figure out which molecules were polar and which ones weren't. Now, you might be thinking, okay, I've got a molecule, but it's not polar. What's helping keep it together? Okay, well, that's where this dispersion force comes into play. This is a really fancy long name. London dispersion forces. It's named after a guy whose last name was London, but the main idea is that it's a dispersion force. Force because it's an attraction, and then dispersion has to do with the spreading of electrons. Basically, anytime you have an atom, it's got electrons roaming around. So there's some electrons floating all around this molecule, right? Occasionally, those electrons, just by pure luck, will kind of arrange to one side like they've done here. See, all the electrons are on this side? Well, if all the electrons are over here, then this side's going to be a little bit negative. And if there's no electrons over here, this side will be a little bit positive. It's crazy. So you can interpret that, this drawing here, I'm interpreting that as just basically, here's an atom, that's the nucleus in the middle, and then that's the negative side, and that's the positive side. Well, this sort of momentary, for the moment, this looks a lot like this has a dipole pointing in this direction, right? Now, it doesn't really have a permanent dipole pointing in that direction. It's not a polar molecule all of a sudden. In fact, this is just an atom. However, because it looks like it has a dipole, it'll attract other molecules around it to do the same thing. Now, this positive charge is going to attract all the electrons to bunch up on this side. This side's going to become negative. So that's negative, this is positive. Oh man, it looks like another dipole. And so this kind of domino effect is called the London dispersion force, and it's what holds normal molecules together. A big thing to know, the strength of this domino effect increases with the size of the atom or molecule, and also just in general with the number of electrons. So for example, let me pull up the periodic table. For example, if I was comparing chlorine and bromine, chlorine is higher up on the periodic table. It only has 17 electrons, whereas bromine has 35 electrons. It's more than twice as many. And so I think it's more than twice as many. Yeah, it is, just barely. So it's twice as many electrons. It's going to have a much stronger dispersion force. So bromine's going to have a stronger intermolecular force than chlorine. But both of them have the same type of interaction because they're both London dispersion forces. Let's see what Sebastian's question is. So kind of like that static electricity generator we used earlier this year. It's sort of like static electricity. You can build up charge basically and then cause that can impose something that you bring it close to draw electrons towards it. Or actually, in this case, push electrons away. Because electrons are negative, they repel other electrons. Okay, so that's London dispersion forces. This is present in all molecules. This is important. Every molecule, every atom, doesn't matter if it's polar or nonpolar, always has this dispersion force. This is just really a property of atoms and molecules in general. Because these atoms and molecules have electrons, and because those electrons move around randomly, then you're guaranteed to have this effect in play. Now, if you have more electrons, or your molecule is bigger, then it's going to be stronger. But in general, this type of force is always around. That's in contrast to the dipole-dipole force. This is only between polar molecules, specifically polar covalent molecules. So that's an important distinction to make. Now, these are the main two intermolecular forces. There's sort of a couple more that are a little weird. So there's a particular kind of intermolecular force that involves hydrogen, and it's called hydrogen bonding. But really, it should just be called like the hydrogen force, because it's not a real bond. It's more just another intermolecular force. So hydrogen force or hydrogen bonding, or H bonding sometimes it's called, this is the strongest IMF. But it only works in very particular circumstances. You need to have a hydrogen atom, and that hydrogen atom has to be bonded. So in its own molecule, it has to be bonded to either an oxygen or a nitrogen or a fluorine. So just these three atoms in particular. So you kind of have to remember which ones these are. If I pull up the periodic table again, they're the ones that are just up here in the top. So N, O, and F. These top three in the top right corner, ignoring the ideal gases. So nitrogen, oxygen, and fluorine. And so because they're super electronegative, basically it's the same thing as a dipole-dipole interaction, but it's even stronger. And so as a result, you end up with a really powerful attraction that does a really good job of keeping the molecule stuck together. So here's a diagram of it sort of happening. So imagine this is like a super polar bond here, where all the electrons are basically next to this oxygen. Then this partial positive charge becomes really close to just a normal, full, big positive charge. And then the negative charge on a neighboring molecule, this attraction becomes really strong. So it looks an awful lot like a dipole-dipole interaction. And it is basically just a dipole-dipole interaction. However, because of this circumstance, because hydrogen is so small, and because oxygen or nitrogen or fluorine are so electronegative, it's just orders of magnitude stronger. And so we give it a special name, hydrogen bonding. So we've covered dipole interactions, which is when you have two dipoles lining up attracting positive and negative ends. We covered hydrogen bonding, which is basically a special case of dipole-dipole interaction, but only if you have hydrogen and only if the electronegative atom is one of these. And then we've covered the generic, boring dispersion force. This is present in every single molecule. So we've done basically all three of the IMFs. Now there is one more, but we don't really talk about it in the same way. It's called ion-ion attraction. This is basically just saying this is what keeps ionic compounds together. So we learned about ionic compounds a long time ago, but for example, you got sodium chloride. You know that sodium has one valence electron, and so it's going to lose that valence electron and become +1. And then chlorine has 7 valence electrons, so it's going to rip that electron off of the sodium and become chlorine -1. And so this +1 and this -1, they form an attraction. And that's an ionic bond. Ionic bond. And that ionic bond is basically sort of like an intermolecular force. However, it's like way stronger than the average intermolecular force. So we call it, we talk about it at the same time. We'll say that it's a stronger attraction than the intermolecular forces. But it's unique to only ionic compounds. So only if there's an ionic bond. So it's not, it's sort of like a separate category. So let's do like a little bit of here's a little bit of a summary table. So dispersion forces are the weakest generally. Dispersion forces are only, they're present in every molecule, but they're not very strong. And they're strongest when the molecule is really big. So if you got some of those giant chemicals you guys built for your molecular modeling project, those would count in the as dispersion forces, and they would have very strong dispersion forces. Dipole-dipole interaction, that's only for polar molecules. Polar molecules only, whereas this is all. So if I was a polar molecule, I would have both dispersion forces and dipole-dipole interactions. And then on top of that, we got H bonding, which is basically a special kind of dipole-dipole interaction that is only true if you have a hydrogen that's bonded to an N, an O, or an F. So a nitrogen, an oxygen, or a fluorine. And then way over here on the spectrum, all the way to the right, you have ion-ion interactions. This is only present in ionic bonds. Okay, so the last thing I want to do is just go over how am I supposed to then take this information and apply it to a problem. So back to this problem I gave you. Let's say I told you you had a CH4 molecule and you wanted to find out which IMFs were holding this bad boy together. So the first thing I need to do is find a Lewis structure. Now, if you don't remember how to draw Lewis structures at this point in the year, well, first of all, I'm sad because we spent a lot of time on it. But at this point, you can just Google it, and it'll come up. So I can just Google CH4 Lewis structure, and I can go to images, and bam, there it is. That's the Lewis structure for CH4. So there's a C in the middle, and there's 4 hydrogens stuck on the outside. So I know it looks kind of like this. Okay. Then I could look this up on my molecular geometry table, and I know that when it's got the 4 bonds like this, it's called a tetrahedral. I should really just type instead of trying to hand draw tetrahedral. If you need access to that molecular geometry table, it's actually posted under Files in Canvas, so you can access it that way. And then because it's tetrahedral and because it's totally symmetrical, notice that carbon is making a bond in all directions to hydrogens. And actually, we consider the bonds themselves to be nonpolar, so we know this is a nonpolar molecule. Nonpolar. So because it's nonpolar, if we go back to our intermolecular forces sort of charting here, of all of these, let me erase the boxes. That's a little confusing. Okay, so we know everybody has dispersion forces every time, always. So without even thinking, I can write LDF. In fact, I could write that without even looking at this next problem. I can write the word LDF here. Looks great. Okay. So then, does this have dipole-dipole interactions? Well, it says dipole-dipole interactions are polar molecules only, but we know that this is a non-polar molecule. So this does not have dipole-dipole interactions. So no dipole-dipole interactions. We know it's not an ionic compound because we know it's an ionic. We know it's a covalent bond. The CH4 is made of covalent molecules. Sorry, it's a covalent molecule made of covalent bonds. So we know it's not an ionic bond. So there's no ion-ion interactions. So the only one to check is H bonding, and this might be true because there is an H, and that H is bonding. So does this molecule have the IMF that's called H bonding? The answer is actually no. So even though it has H's, and even though those H's are making bonds, the bond is not to an oxygen, a nitrogen, or a fluorine. So even though it's got an H, and even though it's making a bond to something else, it does not have H bonding. So there's no dipole interactions, no H bonding. The correct answer is just LDF. And then I'll do this next example too. So NH3, again, I can look it up if I need to. This is ammonia, and it looks a little bit like this. So it's got an H, 3 H's here, and then it also has a lone pair that's sticking out the top. So if you have been practicing your geometry like from last week, you know that this is a trigonal pyramid shape. Trigonal pyramid. What time is it? Okay, I still got some time. Trigonal pyramid. So now we have to determine, is this molecule polar or non-polar? There's a couple ways to check. For me, anytime I got lone pairs in the central atom, I'm thinking it's a polar molecule. And that's right most of the time. But you can also double check that, in fact, nitrogen is more electronegative than hydrogen. So if I go back to my periodic table, and I go properties and up here, and I click electronegativity, I can see that nitrogen has an electronegativity of 3, whereas hydrogen has an electronegativity of 2.2. So I know nitrogen is, in fact, making polar bonds here. So all these dipoles kind of point up-ish. And so that tells me that this molecule overall is polar. All right, so I come to the IMF, the good part. I already have LDF written here. That's weird. And then I remember that every molecule has LDF or dispersion forces available to them. And so you're always going to write LDF for the IMFs. So that's important there. And then now I need to figure out, again, looking at this chart, I know I got dispersion forces checked off. What about dipole-dipole interactions? Is this a polar molecule? And we look back and we remember that we did decide this was a polar molecule. So this indeed does have dipole-dipole interactions. Dipole-dipole. Which, if you'll remember, that's just these molecules are going to line up. When you get a bunch of these NH3 molecules in space, they're going to line up so that all their dipoles are pointing the same direction, which helps attract them together. Okay. Now, we know this isn't an ionic bond because we don't have, if you remember, an ionic bond is always between a metal and a non-metal. And so both nitrogen and hydrogen, N and H, those are both nonmetals. So we know this is a covalent bond. So we know there's no ion-ion attraction. So the only thing left to check is, hey, does this have H bonding? And it's possible it might because there's H's and they're forming bonds. So here's an H. If it's bonded to a nitrogen, an oxygen, or a fluorine, it does have hydrogen bonding. In this case, hydrogen is bonded to a nitrogen. So this extra strong dipole here is going to result in hydrogen bonding. So that is also included. Hydrogen bonding. So I think that's where I'm going to leave it for now. So just remember, dispersion is the weakest, then the dipole forces, then hydrogen bonding, and then if you have an ionic substance, then the ionic bonds are even stronger than that. Every single molecule has dispersion forces. If it's a polar molecule, which is why we spent so long in that, it's going to have polar or dipole-dipole interactions. And then in the special case where you have hydrogen bonding to nitrogen, oxygen, or fluorine, you'll have H bonds. So that's the gist of that. And don't feel bad about having to Google the Lewis structures if you forgot how to draw them. Really, at this point, we're trying to focus on polarity, intermolecular forces, and all that jazz. So yeah.